We are in section 3.3, measures of relative standing and box plots. First term that we have is a z-score or a standard score or a standardized value is found by converting a value to a standardized scale. Is the number of standard deviations at a given value x is above or below the mean. The formula is listed for the population z-score and the sample z-score. They are the same formula, however, one is using the mean and the standard deviation for the population, and the other is using for the sample. Important properties about the z-score. First, the z-score is unitless, and it has a mean of 0 and a standard deviation of 1. Definitely something you need to know. If the data value is larger than the mean, then the z-score is positive, and if the data value is smaller than the mean, then the z-score is negative. A data value is significantly low if its z-score is less than or equal to -2, and a data value is significantly high if its z-score is greater than or equal to +2. The z-score provides a way to compare apples and oranges, different data sets, by converting variables with different means and standard deviations to variables with the same mean, 0, and the same standard deviation of 1. It's very typical that z-scores are going to be around 2 decimal places. The next example says a student takes 2 exams, getting a 55 on test A and a 60 on test B. The class scores for each exams are normally distributed or bell-shaped. For test A, the mean is 50 and the standard deviation is 5. For test B, the mean is 50 and the standard deviation is 12. Find the z-scores of the 2 data sets and compare them. So the first one does ask for the z-score of test A. To calculate the z-score of test A, we need to take your score, or the student's score. We're going to subtract the mean and divide by the standard deviation for test A, and we'll do the same thing for test B. So the score that the student received on test A was a 55, minus the mean that they had for that exam was a 50, divided by the standard deviation for test A, which was 5. Subtracting, you do 55 minus 50, 5, and then 5 divided by 5 is 1. To calculate our z-score for test B, we're going to take the score that we got on test B, which was a 60, subtract the mean, which again is 50, and divide by the standard deviation, which is 12. So 60 minus 50 is 10, divided by 12 is going to equal, we're in around 2 decimal places, it's going to be 0.83. So right below that it says the z-score for test A. So the z-score that we have for test A is 1, and the z-score for test B is 0.83. So the z-score for test A is blank, so it is larger than the z-score for test B. And this means that the student did relatively better on exam A. So the student did relatively better on exam A. We can use z-scores to identify significant values also. Has a mean of 0 and a standard deviation of 1. So as we count this out, I go 2 standard deviations each way. But since I'm adding our standard deviation, I'm going to be at 1 and then at 2. Likewise, going the opposite direction, -1 and -2. And so significant values are those with a z-score less than or equal to -2 or greater than or equal to +2. And again, calculating these z-scores allows us to compare apples and oranges, 2 different data sets. A good example of this would be like if you were to take an SAT and an ACT test and figuring out which scores you want to turn into a college to be looked at. So the next example says the weights of kittens is roughly bell-shaped or normally distributed with a mean of 36 pounds and a standard deviation of 0.4 pounds. The weight of Maria's cat is 2.7 pounds. Is this value significantly low? So to calculate this, we're going to find the z-score. And the weight of Maria's cat is 2.7 pounds. And we're going to subtract away the mean, and the mean for this is 3.6. And we're going to divide by the standard deviation, which is 0.4. And when we subtract first and then divide, we get a z-score, rounding 2 decimal places, of negative 2.25. So is her cat significantly low? So again, remember, significantly low means that that z-score that we have would be smaller than negative 2, and it is. So yes. So yes, it is significantly low. And we'll say because negative 2.25 is less than our cutoff, which is at negative 2. This idea also rolls into percentiles. So the kth percentile, denoted P sub k, is a value in a data set that splits the data into 2 pieces. The lower piece contains k% of the data, and the upper contains the rest of the data, 100 minus k%. So k is going to be a value between 0 and 100. 50th percentile is the median. Many exams use percentiles to let students know how they can score on the exam in relation to all other students who took the exam. To figure out the percentile of a value x, you're going to calculate the number of values less than x, divide by the total number of values, and then multiply by 100%. Then you're going to round to the nearest whole number. So the next example says, explain the meaning of the following percentile. The 5th percentile of weights of males 36 months of age is 12 kilograms. So the first one is 5% of 36-month-old males weigh. They're going to weigh less than 12 kilograms. On the other hand, we have 95% of 36-month-year-old males weigh not less than 12 kilograms, but more than 12 kilograms. And so again, with percentiles, you're always looking at how much less. So since this is a 5th percentile, those are the children that weigh less than 12 kilograms. The next example says the following data represents pulse rates or beats per minute of 19 random students at a local high school. The values are given. Find the percentile of the pulse rate of 71. So we need to count up how many values are under 71. So we have 2 values of 60 here. We have a 68. We have a 65. We have a 68, a 69, and that is everything. I want you to realize there is a 71, but we don't look at that. We only look at the values that are less than. So 6 values are less than the value of 71. So we're going to take our value 6, divide by the total number of values that we have, and we do have 19 students. And then we're going to multiply this by 100. So when we do this, we get 31.58. And we are going to round this to the nearest whole number. So this is going to be rounding to 32. So this is the 32nd percentile. Meaning that 32% of students have a pulse rate under this value, and then 100 minus 32% would have it above this pulse rate. The next definitions are useful, and they get thrown in throughout the semester. So we have quartiles. This is dividing data into fourths, and they're 4 equal parts. The first quartile they symbolize by using Q sub 1. This is the bottom 25% of the data. The second quartile, or Q2, is the median. That's 50% of the data. And the third quartile, Q3, is the top 25. So this is split into equal pieces. So 1, 2, 3, and 4. And each of these pieces is going to be worth 25% of the data. So there's going to be 25% of the data in each of these little regions. So to calculate quartiles, you can do this by hand and putting your numbers in order from smallest to largest and finding the median. And then doing it again for the first half of the data to find Q1, and then doing it for the second half of the data to find Q3. The steps are listed below to do that by hand. But since we do use a graphing calculator, we are going to look at that. So steps to use a TI-83 or 84 graphing calculator to calculate quartiles. So first thing is we're going to go to Stat and Edit. You're going to enter in your numbers into L1. And then we're going to go Stat Calc, go to 1var Stats, and hit Enter twice. You will get, along with mean and standard deviation like we looked at already, but we will have Q1 and Q3. We have seen the median before, but we do have all the quartiles listed on there. So for the next example, we are going to go ahead and circle that, and we will work on that one together in class. The next definition that we have is called the 5-number summary of data values. Consists of the smallest data value, Q1, the median, Q3, and the largest data value. The next example says the data represents the weights of each 2015 men's U.S. soccer training camp member. Use the data and compute the 5-number summary. So the first thing that you're going to need to do is input all of these values into L1 on your calculator. On your calculator, you're going to go to Stat, to Edit, select Enter, and enter in all of the raw data into L1. Next, go to Stat, to Calc, to one variable statistics, select Enter. We have raw data, so you just have to have something written in list, which is L1, which is where our data is. Leave the frequency list blank, select Calculate. And for our 5-number summary, we have our min X value, our Q1, our median, Q3, and our max X value. Those numbers all make up the 5-number summary. From the calculator, we get the minimum X value is 135. That's the smallest weight that we have. Q1, which is the bottom 25%, is 155. Median, which again is the 50%, is going to be 170.5. And then Q3, which represents either the bottom 75% or the top 25%, is going to be 180. And then the max X value that we have, the guy that weighs the most, is 215 pounds. Most of the time, students will just write these out and put commas in between them. That's what our textbook does, and that is totally fine to do. So just listing them all in order. So it needs to go from your minimum value all the way to your maximum value, with Q1, the median, and Q3 in there. The next thing we have is called a box plot. This is a graph created using the 5-number summary. It's also called a box whisker plot. First thing that we have to talk about with this is called the interquartile range, which is denoted IQR. It is the range of the middle 50% of observations. So again, the middle 50% of observations of the data set. And again, subtracting Q3 minus Q1. Then we have an outlier. This is an observation point that is distant from all other observations. It occurs either because of errors, or sometimes it's an extreme observation, and that might happen within a certain population. Right below this is a diagram, and this is a box plot right here. And you will notice that we have our minimum value that we have, and we also have our maximum value. You'll see Q1, the median, and Q3. So we have our 5-number summary is on here. You will also notice we have our interquartile range at the top. That's the middle 50%. Now, all box plots do look slightly different, so something to keep in mind. You will notice that we have outliers that are outside of this box plot, and those are represented by dots, sometimes stars, outside of those little whiskers that we have on here. You also notice that you have some formulas on here with the Q1 minus 1.5 times IQR and Q3 plus 1.5 times the IQR. And those are called our fences, and we're going to get into that right below. So checking for outliers by using quartiles. First thing is to find Q1 and Q3, which is going to be using your calculator. Find the IQR by subtracting those two. Determine the fences, and here's those formulas that we do need to know. So the lower fence is going to be Q1 minus 1.5 times the IQR, and our upper fence is Q3 plus 1.5 times IQR. If a data value is less than the lower fence or greater than the upper fence, then it's going to be considered to be an outlier. And again, we represent that either with dots outside or by using stars. Next example that we have says Anna collects data from the past 12 days on the number of phone calls she receives at work. The number of phone calls are, and they are listed there. Determine if any outliers exist. So in order to figure this out, we need to find our Q1 and Q3 first. So in order to do that, I need you guys to enter in all these numbers into L1. On your calculator, you're going to go to Stat, to Edit, enter in all your values into L1. Next, go to Stat, scroll over to Calc, one variable statistics, select Enter. Your list should be L1 and frequency list should be left blank. Scroll down to Calculate. From here, you'll notice that you have Q1 and Q3 if you scroll down. Those are what you need in order to figure out the interquartile range, and then also to figure out if we have any outliers in our data set. From the calculator, we get that Q1 is equal to 11 and that Q3 is equal to 14.5. So the next thing that we have to calculate is going to be our IQR, or interquartile range, and you get those by subtracting 14.5 minus 11, which is going to be 3.5. From here, we need to calculate our lower fence and our upper fence. For the lower fence, I'm going to go ahead and write LF. And the lower fence is going to be Q1, which is 11. So Q1 minus 1.5 times our interquartile range. So I'm going to go ahead and substitute in all these values. Q1 is 11 minus 1.5 times our interquartile range, which is 3.5. Working this out on your calculator, we do get our lower fence to be 5.75. And what this lower fence tells us is that if we have any data values smaller than 5.75, then they are considered an outlier. And looking at our data set, the smallest value that we had is 10. And so we do not have anything smaller than 5.75. So we have no outliers that are smaller than our lower fence. We also need to look at the larger size. So I'm going to go ahead and calculate the upper fence. So I'm going to take Q3 plus 1.5 times our interquartile range. And Q3 in this problem is 14.5 plus 1.5 times the interquartile range, which is 3.5. Working this out, we get 19.75. So we need to now look at our data set to see if we have any values larger than 19.75. So take a look over at your data set, and we do. We actually have a value. We have 22 here, and that is larger than 19.75. So the value of 22 is considered an outlier. And the reason why is because it is larger than our upper fence. Okay, in order to do a box plot for this, we would have to do what's called a modified box plot. So the modified box plot will be discussed on a handout. So the next thing that we have is steps for drawing a box plot. First thing says determine the lower and the upper fences. Second is to draw a number line long enough to include the minimum, maximum values. Draw a vertical line through Q1, the median, Q3, and create a box with these values. 3 says to label lower and upper fences. And 4 says to draw a horizontal line from Q1 to the smallest data value and from Q3 to the largest data value. Those are also called whiskers. So the next problem says, from the previous example about the U.S. men's soccer team, create a box plot of the data. So I'm going to go ahead and steal the numbers that we had already calculated with our 5-number summary. And so our 5-number summary, which was on one of the previous examples for the men's soccer training camp members, is going to be 135. 155 was our quartile 1. Our median was 170.5. Q3 is 180. And our largest value that we have, our max, is 215. So in order to make our box plot, we need to also come up with our fences. And so to do that, we need to calculate our IQR. And IQR is going to be Q3 minus Q1. So we have 180 minus 155, which works out to being 25. Then to calculate your lower fence, we are going to have Q1, which is 155, minus 1.5 times your interquartile range. Working this out on your calculator, we get 117.5. Likewise, we need to calculate our upper fence. And our upper fence is going to be Q3, which is 180, plus 1.5 times the interquartile range, which is 25. And then working this out, we get 217.5. So now let's look at both the lower and the upper fence and our data values that we have and see if we have any outliers. So you have a couple choices here. You can either go back and look at the data value of these men's weights to see if we have any outliers, or you can look at your minimum value that we have, which is 135. And since our fence is at 117, we don't have anything smaller than that. And our upper fence, which is 217, and we also don't have anything larger than that because our max value weight was 215. So we have no outliers in this case. So in order to create our box plot, we need to draw a line for our axes that's going to represent the values that we're talking about here. And what we are talking about is weights. So you want to make sure you label it, again, communicating what it is that we're showing in our graphs. And with this, I need to look at the weights that we have. The smallest value that I have that I need to include in my box plot is going to be my lower fence, and the largest value is going to be my upper fence. So I need to go from about 117 to about 218. So I'm going to start at 110. And I'm just going to count by tens. So this would be 120, 130, 140, 150, 160, 170, 180. Again, try to do the best you can with spacing them out. We have 190, 200, 210, 220. And that would be as far as I would need to go with this. So the next thing we are going to do is we're going to look at our 5-number summary. And I'm going to put vertical lines for each of these values above, and they kind of float. Nothing touches that axis. So I'm going to put a line at 135. Again, the best that you can do. A line at 155. One at 170.5. One at 180. And the last one goes at 215 pounds. So I have my 5 numbers represented by vertical lines. The middle 3 represent the box. So I'm going to go ahead and make that be a box. And then from my box out to that minimum value and to my maximum value, I'm going to go ahead and draw horizontal lines. So this is my box plot. I am also going to include my fences in this, and my lower fence was 117. Fences are represented by brackets. So there's my lower fence, And then my upper fence is at 217.5, so it is relatively close to that 215. So do the best you can with drawing that in. So this is our box plot. Check to make sure that you have that axis at the bottom labeled as weights.
In order to see your box plot for this, you can go to Second, Y equals, select Enter on Plot 1. You need to turn your plot on. You need to go down to Type and make sure you select the correct graph. It's the 5th one in. Looks like the box plot that we talked about in the notes. Select Enter. When you do that, you will notice that it switched X-list to L1. Frequency needs to be set to 1. Once you have that done, you're going to go to Zoom. Go down to Zoom Stat. On this calculator, it is number 9. Once you have that, select Enter. And you will see that you have your box plot here. You can hit Trace. And once you do that, you will notice that as you hit Trace and you go along the graph, it will bounce from median to Q3 to your max X value, going the opposite direction. We can see what Q1 is and what your min X value is.
So a box plot can often be used to identify skewness. Skewed is going to be if a distribution of data is not symmetric and extends to more of one side than the other. So correlation between box plots and histograms. So when we first introduced that idea of skewness, we were looking at histograms, which is what we have up here at the top. And if you look at the bottom, these are box plots. So a few things to notice is that the first graph, the histogram, is relatively bell-shaped. And that box plot, if you look right below it, the two whiskers are pretty identical. The boxes are pretty identical. You will notice it has some outliers, and those are marked by those stars on the outside of the whiskers on the ends. The second graph, the histogram, is more spread out, and you'll notice that that box on your box plot is also more spread out. The next graph is skewed to the right, and since it's skewed to the right, you will notice that that tail over here, the right whisker, is also longer. And the last histogram that we have is more condensed, and likewise so is your box plot with a few outliers that we have. The next example is one that we are going to work out together in class. So we're just going to go ahead and circle that, and that deals with side-by-side box plots.